Hello, welcome everyone. It is May 30th, 2025. We're in ActInF MathStream 14.1. And here with Jesse van Oostrum discussing a concise mathematical description of active inference in discrete time. This will be a very useful and epistemic discussion. So, Jesse, thank you for writing this paper and coming on. To you to introduce it and start walking us through it.
Yeah, thank you, Daniel. Thank you for the opportunity of being here and allowing me to present my paper. Yeah, first of all, I wrote this paper together with my colleague Carlotta Langer and my supervisor Nihat Ai. We are all in Hamburg at the Institute of Data Science Foundations. And yeah, about 3 years ago, I started getting interested in active inference and wanted to know really exactly how it works, so to say. But this, I had quite a hard time figuring this out, and that's a bit why this paper came about. And maybe I also have some notes here. So maybe I can make very specific my question. So what I wanted to know was, okay, we have an agent who has observations O1 up to OT and has performed actions A1 up to AT minus 1. And then what I wanted to know was an agent acting according to active inference. What will its action AT? How will it choose that? And this question for me was, so with the literature at the time, I found it hard to really pin it down, so to say. So that was the first main objective of making that more clear. And especially also making it clear in a way that is in notation that is very accessible to people who have studied probability theory or any other type of standard mathematics. And yeah, and then throughout the process, a second question came up. So that was the following. So I will go into more detail on this later, but an agent has something that's called a generative model. And how to understand that is as follows. So the world, we can first look at the real world, and that is generating observations. For example, observation 1, the world is in world state 1. Then observation 2. So this is all happening in the world. But then an agent, so this is what we could call a generative process. And a generative model is as follows. So this is some kind of where an agent has maybe some kind of simplified version of what's happening in the world. It is representing in its brain. And from that some kind of simplified world state, it can predict, okay, what kind of observations can I expect from this state? And this is some kind of a very similar model. And in both cases, we can also actually include actions. So if it acts on the world, it will influence its next world, some kind of simplified world state, and the same also here. It will also influence the real world state. So this is called a generative model. And this generative model, it uses it to choose its next action. But then the second question is, how does it learn? How does it learn this model? So this paper is basically, we can basically divide it into two parts. One part is called inference, and the other part, so this is, we could say also action selection. And another part is called learning, the generative model. So this presentation will also be somehow divided into these two parts. So I'll first go further into this first question: how does the agent select its actions? And then also this second, later on, I will go on to in the second part, how is it learning the generative model? And please, if anything is unclear, please feel free to ask questions. If you're now in the live chat or if you're watching this later, you're also always welcome to send me an email or get in touch in another way if you have any questions. I'm really happy. So I wrote this paper for people in my situation 3 years ago who really want to know the exact mathematical details of how active inference is formulated and want some kind of an accessible, easy overview. And if you have any suggestions for improvement, I'm also very open to hear them. So yeah, so that's the basic overview. And what I have to say as well is that this is all, as you saw also from the symbols and stuff, this is all happening in a discrete space, discrete observation space, action space, and discrete time. So there's a whole other literature on the continuous side of active inference. I'm not going into that right now. So that's also not what this paper is about. It's only about the discrete time formulation. Yeah, I'm not sure if we already should stop here for some questions or that I just continue going deeper into the...
Yep, continue. Thank you.
Okay. Yeah, so maybe, so one point maybe I should spend a little bit more time on it is this idea of the generative model. So maybe I write a new one here. So what I think is important to emphasize that these states S are really inside the brain. So we could say this is really in the brain of the agent. And from these states, it's predicting observations. And usually this is some kind of simplified state of the world. And it needs to learn these states without anyone telling it, okay, so maybe in machine learning or something, you're familiar with supervised learning, where you get an observation and then it might learn which state do I have to associate to it. That's not the case here. So the agent really needs to learn itself, okay, what is a good state to somehow encode this observation in so that I can do a useful planning. So this is, you could call unsupervised learning. And there is no way of saying, okay, the real world, for example, is generating observations and therefore this state should be somehow related to that, the real world state. Yeah, and to also maybe make a bit more clear how it can be simplified. So for example, we could have an agent, so we could have a world in color, for example, that like there's all different colors in this world. But for example, an agent that can only see light intensity but no color will have also a simplified state of the world, so to say, so that this will only be black I don't have gray, I see, but this is white and this is gray. So that's just to emphasize this point. Okay, this generative model is really something that's inside the brain of the agent, and it can use it to, for example, plan ahead. Yeah, then I'll go back to the paper. So I will start with some notation. So yeah, so what we are considering is an agent which is going through capital T time steps. So it starts at time 1 and has also some kind of finite time t, and it's performing actions the whole time, and receiving observations. So that we can also see here. So we have observations, and I'm using tau, the Greek letter tau, for any time point, and t for the current time point. So you'll see that appearing more often, this distinction in the paper. And we can use this subscript with the colon to have like a sequence of observations, for example. And then, very important, there's this word policy. And actually, if you come from a reinforcement learning background, this has a little bit different meaning. But here, in this context, a policy is a sequence of actions, and more specifically, a sequence of future actions. So that is sometimes, I find, in the other literature not so clear. But here I want to make that very specific. So we have a policy pi t, and that is actions small t. So there is also small t. So actions small t up to big T. So a sequence of actions, and pi will be then the whole from time point 1. And so usually I write A for actions that are already performed in the past, and pi for the future actions that it somehow needs to do planning on. Yeah, and we have this generative model, which we write like this. And so it's a probability distribution over observations and states given actions, and this theta is the parameter of the generative model. And in this first part, we leave this theta, we leave it out in the notation because we are assuming, okay, it has learned this generative model, and we're just interested in how it's using it. And then in the second part, we will actually look at, we will include it again to see how it's learning this. Yeah, and then also a big part of active inference is, of course, that it needs to infer in what kind of state it is. So what kind, so it has an observation and it has this generative model, and then it somehow needs to infer, okay, what kind of state could I be in? And we use this, that's also in general in the literature, we use this letter Q. So for example, an agent receives this observation 01 and then wants to find out, okay, or express its belief in which state it thinks it is. And that we write, for example, like this. So this is the belief. So this is a probability distribution over states, and it has as information this first observation. And in general, that's always, or we hope that it's approximately equal to the true posterior of the generative model. We will go into this later some more, in how it's sometimes exact and sometimes not. But for now, it's good to remember that this Q is expressing a belief about the state that the agent is in. And we sometimes, so for example, if we, I can also show that here in the paper. So, so this is the actual generative model here. And here we have this belief over states. And what we are doing to make the notation a little bit more concise is to write Qt, for example, Qt of ST, let's say, then this T is implying all the information that it has already from the past. So this is, we can also write it QST given all the observations it has made and all the actions that it has performed. So this T is just saying, okay, we include in this belief all the information, all the observations, all the actions to form this belief, so to say. Yeah, so I think I have discussed now the most important things from the notation. Then I can have a break here also if there's any questions, or otherwise I just continue.
Sounds good. Continue. Thank you.
Okay, yeah. So then we immediately, so that was also one of my goals of this paper, is to immediately get down to this main question, okay, which action is the agent going to perform? And we immediately arrive there already. So the action selection procedure can be described as follows. So we have here a probability distribution over policies. So policies were sequences of future actions. And we say here, according to active inference, an agent selects its next action by sampling a policy pi_t from this distribution and selecting the action AT corresponding to that policy. So I can write it here again. So we have this distribution. For now, we can ignore a little bit what exactly this how this distribution comes about. I will get to that in a minute. But we can just say, okay, there is some kind of distribution over policies, over future action sequences, and we sample some kind of pi_t star. We sample it from this distribution. So we have this pi_t star, which is a sequence of AT star up to AT star. And then we are performing this action, AT star, and yeah, you could say forget about the rest. So this is, all right, I'll do it like this. This is somehow, we are not interested anymore. So we are only performing this action AT star, and then we go to the next time step, get the next observation, and then we'll do this whole process again. So this, for example, this action AT+1 is somehow discarded. So for the next time step, we'll do the process again and then take the first action from that sampled policy. And that, in a very basic way, is already some kind of answer to this first question. Okay, how is it selecting its next action? And what we see is, so it has received these observations and performed these actions, and they also flow into this this probability distribution is dependent on this on these observations and actions. And then the next question is, okay, how does it compute this probability distribution? So that would be the second question to answer if we really want to get down to how is it selecting its actions. And then we see the main ingredient of this distribution is this function g, which is the expected free energy. And I have written one way of writing it, here.
One question there, Jesse.
Yeah.
Why is the policy conditioned on actions from the past when I don't see the A1 through T minus 1 explicitly entering into the unpacking, and policy inference is based upon the observation coming in and how that affects the belief inference, but how does, or why do you have a conditioning on A as well?
So the function g is dependent on a. So in order to compute this function g, we need to know which actions have we done in the past.
Do we though?
Yeah, because it's a bit hidden in the notation here. So we use these past observations to perform inference about, for example, here, our belief in future observations. So in this T here, in the Q, it's captured, okay, this is a belief about future observations, but with the information from observations from the past and actions from the past. It's using those to form the beliefs about the future. Or here, for example, the same for future states. Or here. So in order to make this distribution, what state will I be in the next time step? It is using some kind of belief about what state am I in the current time step, which then again depends on what actions and what observations we have in the past.
Okay, so in practice, the B transition matrix embodies the expected consequences of different actions, but here it's just written in terms of being conditioned upon the whole past sequence of observations and actions that like would have led to that transition matrix being learnt.
Yeah, so here we are assuming that the whole B matrix is already learned, so that we can just take as given, and we only use this O and this A for performing state inference, so to say. So we need to know somehow in what state am I now, and then you can go back and think, okay, what actions did I perform in the past? And then that gives you more information about what state you could be in now. And I wrote this very explicitly because often in other literature, this dependence is somehow completely not made clear. And then I find that sometimes a bit confusing, so that's why I wrote it very explicitly. Okay, in order to compute this distribution, we need this information, so to say. So that's why I wrote it in this way. Does that answer your question?
I think so. I just still don't. I know it's sort of a small thing, but and I see that that you've thought about it. It's just I don't see any of the past time steps in the right hand side. So why would the action have that you took 27 time steps ago other than how it influences how you believe the action to work now, why would the specific memory of the action a given number of time steps ago bear into the calculation now?
So for example, if we take this distribution, right, which is our belief in what state we will be in the next time step, then I think there's many situations where that we can think of that it's relevant what I did 2 time steps before. So for example, if 2 hours ago I decided to fly to Germany, then that will still have influence on where I will be maybe the next hour.
But like in a grid world example, if the transition matrix is the up, down, left, right, the fact that you moved a certain way 25 time steps ago doesn't need to specifically come into play when you're thinking about the next consequences of your action.
So let's say we have a grid world, which is just 1D, let's say. 1D grid world. And you can go left or right. Those are the 2 actions. And let's say this agent knows I'm always starting in location 0. And let's say it, or let's say differently here, let's say here 0, that's a bit easier. And then every action you did in the past will have an influence on in what location you're in now. Right? If for example, we are now at t equals 3, then your location will be different if A1 is left compared to if A1 is right.
But is it conditioned upon your current location and the consequences of action from your current location only? Or is it specifically conditioned upon an action that you took in a past moment, other than how that action resulted in you getting to where you are now?
Maybe sorry, that took maybe very long. So these actions are really the actions we performed in the past. So not any random actions, but really only the one that we performed in the past. Is that your question, or?
The past, yeah, we can continue. I see the past actions matter for changing where you are, and if you're able, and you could do other learnings and so on, but the past actions themselves don't influence where you are or your beliefs about the consequences of action, which are all that come into play in the operational calculation of G. Which doesn't specifically invoke a past.
Up later.
Okay, yeah.
We can maybe postpone it to later to see if we can make it more clear. So so maybe to get back to the so we wanted to know, okay, what is this? What will be the next action? Then we saw, okay, there's this distribution that we sample policies from, and from there we take the first action, and that will be our action. And then we are now looking at, okay, what is this function G that is used for computing this probability distribution. And that function G looks a little bit complicated, so we can just now see what is all coming in to compute this this probability distribution. So we see there is this distributions Q, which are our beliefs about future states and future observations. So those are, and we will discuss later exactly how it can derive these distributions, and they are all dependent on our policies or the next possible actions. So for each different policy, we'll also have different beliefs about what observations we could get in the future. So those are the main ingredients here. And then we have this distribution PC, which is a preference distribution of the agent. And this preference distribution, I also wrote it here, it's completely distinct from the generative model P. So it has nothing to do. So P is a certain distribution, and then PC is a very different distribution. So they have nothing to do with each other in that sense. But it is an ingredient for computing this expected free energy. Yeah, maybe also nice to see. So, for example, this distribution also in the paper of Lenz da Costa and others. We see it here in equation 10. So he also describes it here, and actually
we don't see it. It's just a black bar.
Oh, that's. But you do see the notes, right?
Now it's just the tabs.
And now?
Yeah, still just the tabs.
It is weird.
Yeah, maybe reshare the screen.
Yeah. Did something change or not?
Yep. Okay, now we see the paper.
Okay, great. Sorry about that.
Oh, good.
And now you see the notes?
Yep.
And now you see the other paper or not?
There we go.
Okay,
there
great.
we go.
Yeah. So this is the paper of Lenz da Costa and others, and he has here the same distribution over policies. And then actually in Thomas Parr's book and others, there the distribution is a bit more complicated. They also have an E and an F term, and I'm writing in the paper, I was planning not to go into that now, but I'm writing in the paper here also a note on why they have those terms. But then you can at least see, okay, you can find this distribution in these. I use those two as main sources for writing this paper. Yeah, so maybe people who have already studied some active inference are more familiar with what comes now, but I thought just to briefly discuss this expected free energy and how you can think of it. So we have the equation here, and we see that there are two terms, and this first term is an KL divergence between two distributions. And this first distribution is a distribution over our beliefs in what state we will be in the future, given that we have some observations, which observations are again appearing here. And we compare this distribution, so the beliefs about states, given that we have already the observations, with this distribution where we don't have the observations. And so what you could say a little bit is, if these observations are very informative, then our belief about the state will be very different from when we don't have the observations. So then this difference will be large. But if these observations are not so informative, then these two distributions will be pretty similar, and then this difference will be small. So the size of this difference says, okay, how informative will these future observations be? And these future observations depend again on the policy. So we somehow take an average over what future observations do we expect, given that we have this as next actions, and given that we already have some observations and actions done in the past. So this first term is called epistemic value of information or information gain. And then this second term, we see this preference distribution here come up. So this is the observations that the agent would really like to make. And the distribution here is the observations that it thinks it will make if it is going to do these actions. And so the higher this is, basically, the more likely this policy will give observations that it actually wants to have. So we want this, and that we see also if we go back to this equation. So we see the lower the expected free energy of a policy, the more likely it is that we will sample that policy. And we also see that the higher these two terms are, because of this minus sign, the lower the expected free energy will be. So we want both this utility and the information gain, we want it to be high for a specific policy, or those are policies that we are likely, the agent is likely going to sample. So that is one way to think about the expected free energy. And then another equivalent way of writing it is the following. So here we actually don't have this minus sign. So these terms, we both want them to be small, or the smaller they are, the more likely that policy is going to be sampled. And this term here is an entropy, and it's basically looking at the entropy, or you could also say uncertainty, about the observation if the agent knows the state it's in. So if it's in a certain state, but even though it knows what state it's in, it is very hard for the agent to predict what the observation will be, then this entropy will be high. And then, so therefore also this ambiguity will be high. And therefore the agent prefers to be in states that have low ambiguity. So that's this first term. And then the second term is again a KL divergence, but this time between the belief that the agent has about its future observations given a certain policy, compared to the observations it actually wants to have. So if this difference is big, then it believes it will get different observations from the ones that it wants to have, so that you could say is bad. So this term, which is called the expected complexity or risk, those we want it to be small. So that's a little bit of interpretation on this term, on this G that is used for computing the distribution for sampling the policies and therefore the actions. So there is one more thing is that we can, that is for the computation, nice, so we can make some kind of approximations. We will come back to that later as well in some more detail. And then this G, actually, we can write it as a sum of different, of like single time step G taus. And that makes all the computations a bit easier. And I know that there's much more to write or to say about this expected free energy and where it comes from, but I think that was not the aim really of this paper. So then I refer you to these other sources. Yeah, so now we have discussed this distribution where the policies are sampled from. We have discussed this G, but then an important ingredient of this G, of computing this G, are these distributions Q, Qt. So this belief about future or about states and about observations. And also in the actual, often we are actually interested in these. So not over a sequence of states, but just over one specific time point tau. And I was actually thinking for this podcast not to go into this too much, because I think it's relatively straightforward. So at least what I write here, because I think the philosophy of this whole approach is that we want to use some kind of Bayesian approach as much as possible. And what I have done here is just describe exact Bayesian inference, which would be somehow the simplest way of forming beliefs about states and observations. And then actually in more advanced literature, so to say, you could say that is some kind of an approximation of this exact Bayesian inference. So I would say you could read through this. I can maybe show one small example. So we have this generative model over observations and states given actions. And you could also write this model in this way. And there we see that this model factorizes. So maybe I can just use what I already wrote down. So we see that we can really somehow decompose it into very simple elements where we have a prior over the first observation, this one. We have a distribution that is telling us, okay, if we are in a certain state and we perform a certain action, what state will be the next one? And we have a distribution that is saying, okay, if we are in a certain state, what observation do we expect to get? So those are the three ingredients which are also often referred to as the, maybe I write on this also. So this is called usually called the B matrix. This is called the A matrix, and this I think usually a D vector or something, this prior. So those are the three ingredients for this generative model. And then, for example, so how you would perform exact Bayesian inference is, for example, we say, okay, we first can express our belief in what state we are in. We can just use, okay, that's the prior, which we assumed we already had. And then we then get an observation. So that's why that one is referring to. And that we want, in this case, to be the exact posterior S1 given O1, which is proportional to O1 given S1, and so this is this A matrix, and the prior, or our belief, let's say that's maybe more general, our belief about what state we were in before receiving this observation. So this is a very simple example of belief updating, so to say, which I describe in more detail here in the paper. And I think if you're just starting out with active inference, I think it's quite nice to just think about this whole state inference in this way and think of these other approaches like minimizing some kind of variation of free energy as some kind of approximations to just doing this exact Bayesian inference. Yeah, and that basically concludes all the ingredients we need for describing how an agent is performing its next actions, or how it's choosing which next action it's taking. And so I'm skipping now over this learning part. We will get into that a little bit. And then here in section 4, there's a completely worked out example. So I really recommend, so you might also seen this in, for example, Thomas Parr's book. I've tried to make it very explicit here and very precise, that you can really follow exactly what is happening. And I invite you to just go through this example. So this up till here is just some kind of definition of the model. And then here we say, okay, how it's performing the inferences, how it's making these cues. And then here we see, we compute the expected free energy for all different policies. So this is the first action, this is the second action. So we walk somehow through an example episode of this mouse in this T-maze, which is acting according to active inference. And then second time step, it's updating its beliefs, and then again computing expected free energy, and then again sampling a policy and its action. So yeah, so I invite you to go through that as well. And what I found hard, so I looked at this, there is also, so in order to make these computations, I thought, okay, I really want to make the computations. So I looked into this library pymdp, and also a little bit at the other one, SPM, I think, which is written in MATLAB. But what I found hard was that in both code bases, the actual computations of what's really going on are very deep down in the code, so to say, so are not so accessible. And what I did was actually to write my own code to do these calculations, which is also available on GitHub. So here on the first page is the GitHub link. And what I think is relatively nice from this code is that it's very, so you see the code, right?
Yep.
Yeah. So that it's relatively easy to read. So for example, there's a function sample action, which is exactly, and I have also tried to refer to all the equations in the paper. So for example, here, this is the first equation we've been talking about, this distribution over policies. And here you see exactly how it's computed. So we have to compute for every policy the expected free energy. And in order to have the expected free energy, we need these beliefs over states. And then we have to take this softmax function. Oh, I did not actually say anything about, so this sigma here, that's maybe good to just clarify. This is the softmax function, which makes just these values. So we get for every pi, we get a different value, makes these values into a probability distribution. So for every pi, we have a different expected free energy. We make it into a probability distribution, and then we sample from it. And then we take the first element, basically, of the policy, which is our action, and then we return the action. So I think this code, so if you're just interested, you can play around with it. You can take some parts of it. You can do with it whatever you want. But if the maths are not so clear for you, but it's more clear in code, then you can also have a look at this. So it has the same kind of sequence as the paper. So we sample an action. How's the expected energy computed? We need these two things, info gain and utility. And here we have a part about how it's updating its beliefs, and that's exactly the same as what is described here in the state inference. So this is a little bit different, for example, from the pymdp and SPM, where they use more advanced methods for doing this state inference. But for easy examples, I think this is really more than enough just to get a very precise idea of what is really happening. And then there's also functionality for learning, which we will go into now. So I think that's everything I wanted to say, at least from my side, about the inference. So maybe if there's any questions, I'm very happy to go into those now.
Okay. I could maybe finish covering all the sections of the paper, and then there's a few questions in the live chat, and people can add some more.
Okay, yeah. So for the second part, learning, I was thinking to actually go a little bit more, or to make it a bit more difficult, so to say, and really go into depth of where the equations come from, because for a long time that was actually also unclear to me, and actually quite late in the process it became exactly clear of how where the equations for learning come from. And I think that's also quite a relevant or significant contribution of this paper to present that. And I thought it might be nice for the people who are interested also in where they come from to go into a little bit more depth now. So I would actually say that we go then to the appendix. So there's here appendix B. And we actually first look at a little bit simpler setting to somehow get familiar with the basics, and then we go back to this setting of an agent operating in a world. Yeah, maybe I introduce it a little bit here in the notes. So I'm slightly changing notation now to avoid confusion, but maybe it also makes it a bit more complex, I don't know. So we have now X and Z, and you could basically think of X as an observation and Z as a latent state, I call it. So and maybe I think in most cases you can also think about this as the O and this about the S, so to say, of the model. But that doesn't always hold, so that's why I chose to call it X and Z. And we first, for now, forget completely about this z, and we imagine some kind of very simplistic setting where we are receiving observations x, and we want to somehow make a model of these received observations. So we want to make some kind of probability distribution x. I'm checking which notation exactly I'm using. Yeah. So there's some different observations we can make, 1 up to n. And we want to model the observations we make with a probability distribution which is dependent on theta, and then very specifically, so it is just the probability that we see an observation I given theta is theta I. No. So theta is a vector from theta 1 up to theta n. And the learning, and then you could say learning is finding this theta. And what the active inference literature is suggesting is to think of this theta also, so that is a very Bayesian kind of approach, that we think of this theta also as something that we can have a belief about. So we so we can have also a probability distribution over the theta, which is somehow expressing, okay, I believe, my belief about the theta, that theta I is 0.1, for example, is this number. And that is again, so I'm going to use the bar here. That is again dependent on some kind of hyperparameter alpha, and this distribution is called the Dirichlet distribution, which is a product over the theta i's that we raise to the power alpha minus 1. And so alpha is also a vector from alpha 1 to alpha n. So this distribution, and by the way, there's another paper from Ryan Smith, I think it's also in the references, which also describes this, gives a little bit more intuition about this whole process, which I think is really nice. So I can also recommend looking at that. Yeah, but so this is basically describing our beliefs about our parameters, and then just so we could say the prior belief, and then we can, for example, we make a specific observation x star, and then we can ask ourselves, how is this belief going to change if we incorporate this new information that we made a certain observation? And that I'm not going to all write down, but we can look at here. Let's see here. So what I just described was this. So we have this distribution parameterized, and this belief about our thetas. And then we are interested in this posterior belief, so to say, after having this made this observation x star. And what we can, if you work that out, you see that that's again a Dirichlet distribution, but then with a different alpha. So we call the updated alpha, we call it alpha prime, and this this thing here is the indicator function, which is basically which is 1 when x star is equal to xi and 0 otherwise. So what is happening is that we increase the alpha I by 1, which corresponds exactly to the observation, to the I of the observation, and the rest of the alpha stays the same. And if we look again at this definition of the Dirichlet distribution, so we see the higher the alpha, the more weight that theta I is going to get in the probability distribution. So this is a very, I would say, elegant way of updating your beliefs about the theta when you get new observations. And this is the general idea of how the theta is also learned in the setting that we are looking at in this pymdp, this partially observed Markov decision process setting, where we have states, so hidden states, observations, and actions. Yeah. But so what we were looking at here was just a setting where we had just observations, but we didn't have any latent states. And now the question is, what happens when we do include latent states? So we can do a similar derivation. So we now have two distributions depending parameterized by two different thetas. So we have a prior, which is a vector over the latent states, and then we have some kind of matrix which is saying, okay, given we have a certain latent state, what's the probability of a certain observation? And then we can again ask ourselves this question, what happens with our belief over theta if we get an extra observation? And what is actually the case here is that we get some kind of very complicated distribution, which is not a Dirichlet distribution. So this exact method is not so useful for updating. So this is more like the setting we are looking at, right, where we have observations and latent states. So we have to do something slightly different, and that is that we do by the mean field approximation. And so what we do instead is we let's see how I can best continue. So maybe I go very briefly to appendix A. So in appendix A, I describe some kind of very general, so I think most of you have already seen this, but just for the completeness, a variational free energy minimization approach. So it's described here. So we have some kind of joint distribution, and we want to compute a posterior, which is also the setting we had before. But often this posterior is hard to compute directly. So what we do then is we instead choose a family of distributions, Q, and find, so these Q tildes are all elements of this Q, and we try to find that Q tilde that is minimizing this expression. And that Q we call Qx because it's actually dependent on this X, on the observation that we made. And this is some kind of very general approach, which is called the variational approach. And that is somehow used to approximate a posterior that we can't compute directly. So that is described in more detail here in this appendix, and also how it plays a role in active inference. I think for time reasons, I won't go into that much deeper now, but just to describe this method at least. So we use that same method also here. So right now we are dealing with latent states, so these z's that we don't know, and we are dealing with the parameters that we don't know. So we somehow, but what we do know is the observation and the hyperparameters. And we want to find a distribution over the latents and the parameters. And then we use the same variational free energy minimization approach, where we are trying to find a Q that is minimizing this distribution. And then what we do, what I was also saying before, often we restrict the Qs that we can choose from, which is, and in this case, we are only looking at Qs which can be written as a product of these individual distributions. So that's some kind of an approximation that we are making here, which is called the mean field approximation. And if we do that, then this equation simplifies a bit. And what we also do, so this is a very important insight, is that it's quite hard to minimize both of these Qs at the same time, because they are both influencing each other. And there is a specific algorithm called the CAVI algorithm, coordinate ascent variational inference algorithm, which is saying, okay, instead of trying to find both at the same time, we start by fixing one and then optimizing the other, and then use that. So for example, we start by fixing this Q theta and then find QZ, and then use this newly found QZ to find a Q theta, and then you can do that iteratively and hopefully get to the optimizer. And that is also exactly the approach that is used for learning in active inference. So very specifically, we first have some kind of prior belief about our generative model, about the parameters of the generative model. So we fix those that belief, so to say, or those parameters. And with those parameters, with the generative model, we can do inference, like we looked at before, like this Bayesian inference. And that's also what's done here. So we get some kind of QZ. So this is a different way of describing inference in terms of variational free energy. But what's done here is we are just trying to infer what kind of latent state are we. And we have fixed the parameters Q theta. So, and then we have this QZ, so this belief about the state we are in. And then we are somehow where we want to be. We want to find this distribution Q theta. And then we use this fixed QZ to then optimize this distribution, which is only dependent somehow on Q theta, and the QZ is fixed. And if you would really want to find the minimizer, you would continuously be doing this, alternating these two steps. What is very important to note here is that the active inference literature is saying our update is only doing the first step. So we only do the first step. We do one time state inference, and one time we optimize this parameter, belief on the parameter given this state inference, and then we stop. So that is, so it's not exactly the same as the CAVI algorithm, but you could say it's only the first step of the CAVI algorithm. And so here I'm describing what does that minimizer then look like, and that is given by this basically the exponent of the term that's here. So you can also see that if we take the exponent and we take the log, we just get what's there, and then it's minus what's there. So that is the minimizer, so to say. And I'm using these terms C with the backslash to say, okay, these are all terms independent of the argument, so we don't have to worry about them for the minimization. So here we have a very specific form of the updated belief in our parameter. And then we can use the fact that we are actually working with this Dirichlet priors and this categorical model. And then we can, so that P here, that was defined here, so in terms of these thetas and in terms of these Dirichlet's. And what you see then is that this updated Q after the first step in this algorithm looks like this. And this is exactly, again, a Dirichlet distribution. So that's a really nice result. So I didn't make any assumption that it has to be a Dirichlet distribution. I only said, okay, we do this mean field approximation, but it comes out that it is, if you only do the mean field approximation, that this first step of the CAVI algorithm is again a Dirichlet distribution. So we can formulate the update again in a very elegant way like this. So we just add something to these two updated alphas. And what we add exactly is the following. So for example, this alpha D is related to the theta D, which is the belief about the prior belief in the latent state. And we add the belief after doing the inference that we are in that state. So this is in some sense a very similar update to this update here, where we are just adding one for the observation that we did, but now we are not adding one for the observation, but we're adding only the belief that we are in that state to the original alpha. And something similar here, where we add the belief in the transition, more or less. So yeah, I can imagine that this was a little bit fast and maybe a little bit abstract because there were not so many examples, but I felt this for the people who really want to know, okay, where do these equations come from? I think this is quite a relevant contribution. And so what I was talking about now was only these x's and z's. The notes are still there, right?
Yeah.
Great. And now we want to translate this to this setting where we are actually having this S and the A's and the O's. So then the equations get even a little bit more complicated. So I thought it was good to have this build up to first see, okay, what is the general principle, this mean field approximation and the Dirichlet coming out. And then you can apply exactly the same procedure to this more complicated setting where we have this full generative model. And then you get this derivation here, which I'm not going into now. But there we see again at the end that we have a Dirichlet distribution. And here you see, okay, alpha, we have to add this to the alpha. We have to add this to the alpha A. We have to add this to the alpha B. And then we get, so this is the main part of the paper. We have these updates here for the learning. So yeah, so for the people interested in knowing where do these learning rules come from, there is this appendix B, which I went through now a little bit quickly and maybe a little bit high level, but yeah, you can look at that in more detail or ask me questions about it if you are interested in this. And maybe to just link it to the other literature. So here this is the book of Thomas Parr. There's this appendix B23 learning. And here he is coming to the same equations, but using a bit different method that I found hard to follow. So yeah, but these update rules, they are also here, and the same also in this paper. Let's see if the reference. Yeah. So here we also have these updates, but also using a different method than the one I'm using. And actually this method that I am presenting is referred to me by Connor Hines. So thanks very much for pointing me to this derivation, because I think this, for me at least, is the most clear one I have seen so far. Yeah, so far about learning. So there's one I would be able to, if their time allows, could go briefly over the appendix A, but maybe we also first take some time to for questions about this learning part, and I'm also fine with not discussing this appendix A.
Awesome. Okay. I will ask some questions that were submitted by Arun, and then if anyone else has any questions, they can go for it. Okay. First question. Do you intend the accompanying repository to be a static accompaniment to the paper, or do you see it evolving, for example, adding habitual policy selection to the agent via eTensor?
I would say from my side, I'm not really planning on developing it further, but if people want to, I am very happy, for example, if they fork the repository, copy it in any way. Would be nice if you reference me if you still use it. But yeah, so from my side, I don't see any further developments, but I would be very happy if other people want to actively start using it. So please get in touch if you want to.
Cool. Okay. Would it be possible to further document the flattening class, at first with comments, but ideally with unit tests?
Yeah, so that is indeed so maybe a good point to make about the code. So in pymdp, there is some, I have that also here in appendix C, I think. There is some extra kind of structure being put on, for example, these conditional probability distribution. So, for example, we say the location in the next time step is independent of the reward condition in the previous time step. And that is, for the computations, it's very nice because the computations get a bit easier. But the code gets a lot more complicated, and you don't see, especially because, for example, here, if we look at all these, for example, get believe next states. Yeah, I think that's a good example. Update believe current state, something like this. For example, this one. This is very simple and elegant, I would say, and that is because I am ignoring that, so to say, in the code, that there exist these independencies, and I did that on purpose to keep the code as simple as possible. But what is then a bit harder is that, what pymdp is using is having some kind of state which is somehow multi-dimensional, and then also, for example, the A matrix, let's say, which is I think some kind of list. So in the observation state, so there's observation modality state vector. So these are both can have multiple elements. So this is a list of matrices, and these matrices, so for each modalities, let's say, each modality M, and this is then again some kind of tensor where we have here the observations for that specific modality, but then we still have here also for every state vector a different dimension, so to say. And in my case, what I am doing is just saying, okay, we just say that the state space is, let's say, one dimensional, and we just have S1, 1, S1, 2, let's say there's two state vectors, and I'm just putting them all into a long list, so to say. So that's what I call flattening. And then this A matrix is just one matrix where there's all the flattened states here, let's say S flat, and here O flat. And that makes the code very easy, but there I do need something to translate between the pymdp states, which are somehow have these different state vectors, and the flat states that I am using. And that is indeed, I agree, is not the best documented code. So I wrote that, and then I tucked it away in this flattening class, and was hoping that everyone would believe me that it works well. But we could talk about it, because I do think it's a good point that it would be nice if it has if you don't just have to believe me that it works, but that you can actually check it yourself. So maybe you can send me an email and we can discuss how to best document it.
Yeah. Lots of little challenges with matrix format and
Yeah.
small things that, yeah, definitely. Okay, I'll ask Aaron's last question here, and this is kind of a good final discussion piece, which is, what do you see as the next key area to tackle in terms of increasing the clarity of how active inference works?
Yeah, that's an interesting question. So I felt that with this paper, most of the questions I had were answered. I'm now looking a bit together with Lance da Costa also at how well, for example, these learning rules in practice are actually performing. But that is maybe different from so I feel, at least in my opinion, in the paper, it's clear how they are formulated. So I would say, yeah, I would be open for suggestions, but I have answered with this paper most of the questions, at least I had, about how active inference works, and then of course about this very specific domain of the discrete time domain.
Yeah,
Of course, there's
what did you think, or have any conversations about how this relates to the continuous and the path-based versions?
So I have actually only spent time with the discrete setting. So I think, in the beginning very optimistic. I thought, okay, first understand the discrete and then the continuous. But then I first spent time on understanding it, and then I thought, okay, let me write this paper on it, which also took quite some time. So I actually have no experience with the continuous case. I'm not sure. Lance is not here, right? Or
No.
otherwise we could ask him. But he is more familiar with. So I think that's more a question for him. Maybe he is at some way able to answer that at some point.
Cool. What are your next steps, or how are you gonna move forward, having satisfyingly reduced your uncertainty about discrete states?
Yeah, so I am very interested in general in this. We could maybe call it A/B learning domain. So how is an agent actually learning these matrices? So together with Carlotta, with my colleague, we were also applying this framework to study consciousness, or are still busy with that, and a paper about it hopefully coming out soon, where we use an active inference agent and then look at how its integrated information is developing. And but we saw actually in the environment that we were using that it was very hard for the agent to learn the A and B matrices, or learn an A and B matrices that allows it to operate well in the environment. So for me, that's the next big question, is what is actually, are these learning rules from active inference the right ones, or are there other rules that are maybe more effective and maybe more probable? So that is for me a big question that I completely don't have an answer to right now, but is really, I find really fascinating.
Awesome. Any other comments you'd like to make?
So I think it's good to finish it here, but just to say that there's also this appendix A. So maybe a bit weirdly, but I think all of free energy and active inference usually is formulated as a minimization of this variation of free energy. But starting the story from there, I find then it gets very confusing most of the time. But I do write here in Appendix A how everything that's written in this paper can also be related to this bigger idea of minimizing a variational free energy function. So you can just read through it here, perception, learning, and action selection, how they are all related to minimizing this function, just so you know that it's there.
Awesome. Well, again, thank you for the important and pedagogical work. I look forward to many in this genre.
Thank you so much for the opportunity. And again, if anyone has any questions or wants to reach out, please feel free to do so.
Awesome. Thank you. See you.
Thank you.